Welcome back. In our last lecture, we looked at discrete I/O modules, which handle simple on and off signals. Today, we'll continue with Chapter 2 and move into analog input and output modules. Unlike discrete devices, analog I/O allows us to measure and control values that vary continuously, things like temperature, pressure, flow, or motor speed. We'll also explore several special-purpose I/O modules that have been developed to meet the unique needs of different industrial applications. By the end of this lecture, you'll see how these modules expand a PLC's capabilities beyond basic on and off control to handle real-world processes with precision. Analog input and output modules are used whenever the control process requires values that change continuously, rather than the simple on-off signals of discrete I/O. As shown in this figure, common analog inputs include sensors such as temperature sensors, potentiometers, and ultrasonic or proximity sensors. These devices measure real-world variables and send continuously variable signals into the PLC. On the output side, the PLC can use analog signals to control devices like valves, meters, and stepper motors, which need precise adjustments instead of just full on or full off states. A good way to think about the difference is to compare a light switch and a dimmer knob. A discrete input-output is like a light switch. It's either on or off, nothing in between. An analog input-output is like a dimmer knob. It can smoothly adjust the brightness to any level in between. Similarly, analog modules allow the PLC to regulate temperature, flow, or motor speed with fine precision, rather than just turning things on or off. Unlike discrete devices, which can only be on or off, analog input and output devices can represent an infinite number of values. This makes them essential for measuring and controlling real-world variables like temperature, pressure, or fluid level. There are two basic types of analog input modules: voltage sensing and current sensing. Voltage sensing modules measure varying DC voltages, while current sensing modules measure current signals. This figure illustrates how PLC analog modules are used to measure and display the level of fluid in a tank. The level transmitter produces a variable signal that reflects the height of the liquid. This signal enters the analog input module, which converts the analog signal into a digital form that the processor can understand. The processor then uses the program logic to decide how to respond and sends a digital command to the analog output module. The analog output module converts this command back into a variable analog signal, which in this example drives a level indicator to display the fluid height. Now, let's examine some special types of analog modules. High-speed counter modules are designed to capture pulses from sensors, encoders, and switches that operate at very high speeds. Unlike standard input modules, these counters contain their own electronics that allow them to count independently of the PLC processor, ensuring no pulses are missed. This capability is critical in applications like motor speed monitoring, position tracking, and machine feedback systems where inputs may occur much faster than the processor's scan cycle. A typical high-speed counter can handle rates up to 100 kHz, which means it can count as many as 100,000 pulses per second, providing the accuracy needed for high-speed automation processes. The thumb wheel module allows operators to enter numeric values directly into the PLC using thumb wheel switches. Each wheel is set to a digit, and together they form a number that can be read by the PLC and used in the control program. This makes it a simple and reliable way to feed set points, batch quantities, or timing values into the system without needing a computer or complex interface. For example, an operator could use the thumb wheel to enter the desired number of parts to be produced, and the PLC would use that value as part of its program logic. Thumb wheel inputs are especially useful in older or cost-sensitive applications where durability and ease of use are priorities. An encoder counter module allows the user to read the signal from an encoder on a real-time basis and stores this information, so it can be read later by the processor. An encoder is mainly used for feedback purpose to know the position and distance measurement in process applications. Encoders convert motion to electrical signal pulses. For example, if a rotary encoder is designed to produce 100 pulses per revolution, Each pulse would indicate 3.6 degrees of rotation. Motion and position control modules are used in applications where accurate, high-speed control of movement is required, such as machining, robotics, and packaging systems. These modules allow a PLC to interface with stepper and servo motors, providing precise control over both speed and position. As shown in the diagram, the PLC sends commands through the servo drive, which powers and controls the servo motor. Feedback from an encoder is sent back to the PLC, allowing the system to make real-time adjustments and maintain accuracy. By integrating inputs, outputs, and feedback, motion and position control modules enable highly precise, automated motion in advanced industrial processes. A real-world example is a CNC milling machine, where the PLC must move the cutting tool to exact coordinates with precision. Another common use is in robotic arms on assembly lines, where motion control ensures that parts are picked, placed, or welded in exactly the right spot. Without these modules, such high-speed and highly accurate automation would not be possible. We've now seen how discrete and analog I/O modules bring information into the PLC and send signals back out to control devices. In the next lecture, we'll take a closer look at the CPU, the brain of the PLC, to understand how it processes this information and makes the control decisions that drive the entire system.